All right, so welcome. We are on page number 18 of your notes in the practice in the back of your notes. And so this is where we're going to be drawing Lewis dot diagrams of different compounds, different molecules, and then we're going to determine whether the molecule is polar or nonpolar. So remember, if you're asking about the molecule being polar or nonpolar, this is where I like to say, this is where molecules synapse together, which stands for symmetrical is nonpolar, asymmetrical is polar, right? Because when we're talking about symmetry, right, when polar means different, when you have lines of symmetry and you have differences in the molecule, you have a polar molecule. If the molecule is symmetrical, then you have a nonpolar molecule. So let's do our first one. So we have to start with Lewis electron dot diagrams. We need to have our valence electrons. Nitrogen has 5 valence electrons. So I have 2 nitrogens, each with 5 valence electrons. So I'm going to just draw my 2 nitrogens next to each other, and then 5 valence electrons. The first 2, 3, 4, and 5. 1, 2, 3, 4, and 5, right? The first 2 go together, and then one at a time, and you only partner them up unless you have to. And so what I like to do now is I like to circle my unpaired electrons between the 2 nitrogens. So I have one pair here to share. I have another pair here to share. And now I have these ones on the outside. Can I still share those? Absolutely, because this is a 3-dimensional thing here. And so now what I ended up doing is I still have my 2 nitrogens. I made 1, 2, 3 circles. So I made 3 bonds, right? Each one of those lines represents a pair of shared electrons. And now I still have 2 lone pairs. I'm going to put those on the outside, right? Because we want to spread them as far away from each other as possible. Now when I take a look at this molecule, and I draw a line of symmetry this way, it is symmetrical. And if I draw a line of symmetry this way, it is also symmetrical. So this is a non-polar molecule. And just quickly review what kind of bonds. I have 2 nitrogens, each with the same electronegativity, right? The same 2 elements. This is going to be a nonpolar bond. And because it's symmetrical, a nonpolar molecule. Now, to check if I'm right, I know that nitrogen on my periodic table is 3 places away, 5 valence electrons, 3 electrons away from having a stable electron configuration. So I know nitrogen needs to make 3 bonds. Did I make 3 bonds between my nitrogen? Yes. So I do have my 3 bonds, right? I have 3 pairs of electrons shared. They're shared equally because it's a nonpolar covalent bond. So now let's look at our water molecule. So now I know that hydrogen, each of these hydrogens has 1 valence electron. So I'll just do 1 and 1. And an oxygen has 6 valence electrons. Remember, the valence electrons are the last number in the electron configuration on your reference tables, on your periodic table. So I'm going to put my hydrogen can only make 1 bond, so it can't be in the center. I can't have a hydrogen with an oxygen attached and another hydrogen attached to a hydrogen. So I'm going to attach the hydrogens to the oxygen. So oxygen has 6. 1, 2, 3, 4, 5, 6. And so now I have my 2 open spots. Oxygen has to make 2 bonds. Hydrogen each has to make 1 bond. So I'm going to put a hydrogen here with its 1 valence electron, and another hydrogen here with its 1 valence electron. So now I'm going to circle my unshared pairs, and then now I can draw that. I have my oxygen. Now I have a bond to 1 hydrogen and a bond to the 2nd hydrogen, and then I still have my lone pairs. So here I have a polar bond, right, between the oxygen and the hydrogen, two different nonmetals, right, two different electronegativities. And so since this is asymmetrical, this is going to be a polar molecule. And I like to say water is polar because polar bears swim in it. It's one way to remember that water is polar. And water is asymmetrical distribution of charge because it is symmetrical in this direction, but it is not symmetrical in more than one direction. And so when we have a polar molecule, we have partial charges. We do our partial negative charge on the higher electronegative element. How do you know which one is the higher electronegativity? You look on table S, and I have my partial positive and my partial positive. It's like making an incomplete 8. That's how I like to do my lowercase deltas. All right, so now let's do, we have carbon and oxygen. The least electronegative element will be our center, right? Carbon has a lower electronegativity than oxygen, right? I have a polar covalent bond, so I'll just do PC bond. Carbon has 4 valence electrons, and each of these oxygens has 6. So carbon has its 4 valence electrons, so 1, 2, and 3, and 4. Try to make my electrons look prettier. And now I have 2 oxygens, so I'm just going to put an oxygen over here, and I'll put an oxygen over here. And each of these has 6 valence electrons. So 1, and 2, and 3, 4, 5, and 6. And 1, 2, 3, 4, 5, and 6. Okay, so I put the ones that are partnered up on the outside because I know I'm going to need to do some sharing. So I can share unpartnered electrons between the carbons and the oxygens, but not between these oxygens over here. So I'm going to make a partner share here. There's 1 bond, and then there's 2 bonds. So I know each of these oxygens has to make 2 bonds, right? Because it has 2 open spots. It needs 2 more electrons. It's 2 spaces away from the noble gases on the periodic table. Carbon has to make 4 bonds, right? Because it has 4 valence electrons, it needs 4 more, and it is 4 spaces away on the periodic table from a noble gas, so 4 bonds. Right now, my carbon only has 2 bonds. Each of these oxygens only has 1. So now I need another share. I can share these right here. And then now I have this one, and it's still between the carbon and the oxygen, so I can do that. And so now I'm just going to redraw this to make this look prettier. I have carbon, and I made 2 bonds to the first oxygen, and I did 2 bonds to the second oxygen. And now I have to still do my lone pairs. So I have 4 electrons here, and then I have 4 electrons here. I'm just gonna draw a line so that it separates them. I shouldn't have drawn them so close. Okay, so now I have polar covalent bonds between the oxygen and the carbon, right? Because 2 different nonmetals and electronegativities. But now I need to figure out what is this molecule. So is this molecule symmetrical or asymmetrical? So I have a line of symmetry down the center. I have a line of symmetry across the center, and it's symmetrical in both directions. So this is symmetrical. So that means there's no differences when you look on either side of your lines of symmetry. So non-polar molecule. Right, so I have polar bonds, but they've arranged themselves in such a way that this is going to be what we call a linear molecule. Right, and our water over here, we call this a bent molecule. And then anytime you only have 2 things together like this, it's linear, if we're talking about shapes. Right, let's take a look here at ammonia, NH3. Nitrogen has 5 valence electrons. It means it needs 3 more. It has to make 3 bonds. Hydrogen has 1 valence electron. Each of those hydrogens have to make 1 bond for a total of 3 bonds to the nitrogen that also happens to need 3 bonds. So I'm going to draw my nitrogen with its 5 valence electrons, 2, 3, 4, and 5. And notice how convenient. It has 3 open spots, and I have 3 hydrogens to place. So there's my one hydrogen with its one valence electron. There's my second hydrogen with its one valence electron. And there's my third hydrogen, with its one valence electron. And so now I'm going to circle my unpaired electrons. And so I've made 3 bonds for nitrogen. Each of the hydrogens has 1 bond, so that satisfies our octet rule, right? So nitrogen has 2, 4, 6, 8, right? So every element has to have 8 electrons, right? Just making sure from our carbon up here, right? So carbon has 2, 4, 6, 8. Oxygen has 2, 4, 6, 8, 2, 4, 6, 8. Okay, so then now let's just make this a little bit prettier. So making our circles into a line, right? Every line represents a shared pair of electrons. And don't forget this lone pair right there, that's very important. So here I have a molecule, and again, I have a polar covalent bond, right? Because that's between the hydrogens and the nitrogens. Now, in terms of the molecule, I have to look at the shape and see if this is symmetrical or asymmetrical. So when I look down the center, it's symmetrical down the center, but right, vertically, but not horizontally. So this is asymmetrical. Right, so when I did that center line of symmetry, right, horizontally, right, I have 2 electrons on the top and a hydrogen on the bottom. That's not symmetrical, right, that's different. So it's asymmetrical, polar, right, because when I snap with the molecules, symmetrical, nonpolar, asymmetrical, polar. And now let's do our partial charge. I have the partial negative charge because the nitrogen has a higher electronegativity. And I have partial positive charges. Because remember, this is a tug of war for electrons. The nitrogen has a stronger pull, so they're getting pulled in towards that nitrogen, making it partially negative. It only happens in a polar molecule because it's the distribution of charge that makes it not symmetrical. So with our with our carbon dioxide, it's getting pulled in these opposite directions, so it kind of cancels each other out. It makes the symmetrical distribution of charge for the carbon dioxide. Now let's look over here at our CH4. This is our methane gas. Carbon has 4 valence electrons. It has to make 4 bonds. Hydrogen has 1 valence electron each, and it needs to make 1 bond total for each hydrogen, so 4 bonds. So carbon will be our center atom. And because hydrogen can't be in the center, because hydrogen can only bond once, it can only form 1 bond. So here's our carbon. And now I'm going to place my hydrogens at the open spots, hydrogen here, and hydrogen here, and hydrogen here, and hydrogen here. And now I'm going to circle, and circle, and circle, and circle. Now let's pretty it up. Right? Every time I've circled, that becomes a line that's a bond of indicating the 2 shared electrons. So then here I have a polar covalent bond because carbon and hydrogen are different nonmetals with different electronegativities. But my whole molecule here, now let's take a look and see our molecule. If it's symmetrical, it's nonpolar. If it's asymmetrical, it's polar. If I look at this molecule, it is symmetrical in every which way direction. So this is symmetrical. So symmetrical is non-polar, right? The distribution of charge is symmetrical, right? The charges are being distributed equally amongst the whole molecule. All right, so we're not going to do that one. So let's go back up to the top here to number 7. So now we have hydrogen with its 1 valence electron and fluorine with its 7. Hydrogen has to make 1 bond, fluorine has to make 1 bond. So I have my hydrogen with its 1 valence electron, and I have my fluorine with its 7. 2, 3, 4, 5, 6, and 7. Circle my unpaired electrons. So then that forms the bond. You have to make sure that you redraw these lone pair electrons over here. Very important. It's not a Lewis electron dot diagram if there's no dots. So now here I have a polar covalent bond, right? Because I have 2 different nonmetals with different electronegativities. And now this is not symmetrical because if I draw a line of symmetry down the center, I have hydrogen on one side, fluoride on the other side. That's not symmetrical. So this is asymmetrical. And remember, SNAP, symmetrical, nonpolar, asymmetrical, polar. So this is asymmetrical. So that means it's going to be polar, right? Because polar means different. It means I have a partial charge. I have a partial negative charge on the fluorine. Because remember, all the electron pull is stronger towards the fluorine. So more negative on this side. That gives us this partial positive on that side. All right, so now I have carbon, hydrogen, oxygen, hydrogen. So then I know carbon loves to be in the center. It has to make 4 bonds. And hydrogen can't be in the center. It has to be on the outside. And I know oxygen needs to make 2 bonds. So then hydrogens have to be on the outside. And now this means that the hydrogen is attached to that oxygen. So I'm going to have an oxygen and a hydrogen. And let's just do my bonds here. So I'm going to have those 4 for carbon. Each of these has 1 valence electron. Each of these has 6, and that one has 1. So 1 valence electron. And now let me draw the 6 for oxygen. 1, 2, 3, 4, 5, and 6. Okay. Let me just make my dots look prettier. Yeah, they don't look pretty. And now I have those 3 hydrogens. So I have a hydrogen here, and a hydrogen with its 1 valence electron here, and another one here. So then I can circle this one, this one, this one, and this one. So carbon has been satisfied. It has 4 bonds. Each of these hydrogens have made 1 bond, so they're satisfied. Now I can circle this one here. So now oxygen has made 2 bonds, it's satisfied, and hydrogen has made 1 bond, it is satisfied. So now I'll redraw it. So I have carbon, and I made a bond to a hydrogen. I made a bond to a hydrogen. I made a bond to the hydrogen, and then I made a bond to the oxygen and to the hydrogen. And let's not forget this right here. So then here I have polar covalent bonds, and then I have a polar molecule because it's definitely asymmetrical, right? Because I've got an OH on one side and an H on the other side. So obviously I'm asymmetrical. So now here I have H2S, hydrogen with its 1 valence electron, sulfur with 6. So hydrogen has to be on the outside, so sulfur will go in the middle. So 1, 2, 3, 4, 5, and 6. So now hydrogen has a spot to go here, and hydrogen has a spot to go here. And so I will circle this one. I will circle this one. And so now I have my sulfur, and I made a bond to the hydrogen, and a bond to the hydrogen, and then I have my 2 over here. So here again, polar covalent bonds. But now my molecule, and again, this is a bent molecule, just like the water molecule was, right? Which makes sense because sulfur and oxygen are in the same group. So it's going to have similar bonding between the 2 because they have the same valence electrons, right? So it is asymmetrical. So this is polar. And then the sulfur has the higher electronegativity, so it's got the negative charge, positive, partial positive charges. All right, so let me just quickly go back up to the top here, number 7 here. So when this is going to be a linear shape molecule, because I just have those 2 things, it makes a nice little line here. And then anytime you've got carbon, you have, let me just go down over here. This is the tetrahedron shape. So you do need to know that carbon, the 4 methane with the 4 carbons makes a tetrahedron shape. And then this is what we call a pyramidal shape. For the Regents exam, you don't need to know the shapes. You do need to recognize the word tetrahedron though, when in reference to carbon though. Okay, so I have iodine. Each of these has 7 valence electrons. Each has to make 1 bond. I have 2 iodines. Each has 7 valence electrons. 2, 3, 4, 5, 6, and 7. And I just want to line them up in between. So the empty one because it just makes it prettier. And I'm going to circle my unpaired electrons. And my iodine forms a bond. And don't forget those extra electrons, right? They're still important. So here I have a non-polar covalent bond because I have two of the same nonmetals with the same electronegativity. But now let's take a look at our shape, right? Our shape has two lines of symmetry. So this is symmetrical. So symmetrical is nonpolar. So this is also a nonpolar molecule. All nonpolar covalent bonds make nonpolar molecules. But polar covalent bonds can be either polar or nonpolar. And this whole idea of polar and nonpolar molecules is a really large part of biochemistry, which is important when you get into upper levels of biology. So I have carbon has 4 valence electrons. I know it has to make 4 bonds. If it has to make 4 bonds, it's going to go in the center. I know hydrogen cannot go in the center. So I know that hydrogen is going to have to go over here. And now I've got 3 chlorines, right? Because I've got 4 things to attach to the carbon. So I'm going to have a chlorine, and a chlorine. So carbon has its 4 valence electrons. Oh, the one on the bottom I made kind of looks like a heart. And then hydrogen has 1. And chlorine has 7. 2, 3, 4, 5, 6, 7. All of these chlorines have 7. All of the chlorines have 7. My drawing tool isn't perfect, so my little dots, so circle and circle. Then I can make one here, and I can make one here. So I have carbon to a hydrogen to a chlorine with all of those extra dots to another chlorine with all of those extra dots to another chlorine with all those extra dots. And so here I have polar covalent bonds, right? Because I have 2 different metals with different electronegativities. I'm sorry, not metals, nonmetals. But now if I take a look at my molecule here, this is asymmetrical, right? It's not symmetrical like this one over here, the methane, because if I draw this line of symmetry horizontally, I've got a chlorine on the bottom and a hydrogen on the top. They're different, right? Chlorine and hydrogen are not the same. So different means polar, asymmetrical. So this is a polar molecule. MOLEC for short. All right, now our last one, oxygen. So this is our nonpolar covalent bond because I have 2 of the same nonmetals with the same electronegativity. So I already know if it's a nonpolar covalent bond, it's going to be a nonpolar molecule. And again, this is also a tetrahedron shape over here because, right, tetra means 4. So now I have oxygen, and I have an oxygen. I have 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and 6. I know oxygen has 6, right? It needs 8, right? It needs to make 2 bonds. 1 and 2. So when I draw this over to make it look pretty with my lines instead of my circles and dots, I have my 2 oxygens, and it has the 2 pairs, 4 total electrons shared, right? There's 4 electrons in my circles. And don't forget my lone pairs, very important, right? They are still part of this molecule's Lewis dot structure. And this is symmetrical because there's more than one line of symmetry. So this is symmetrical, nonpolar. Okay, so just a little bit of trick that I'm just going to jot down over here. If the last element is an odd number, it's most likely polar, right? Because odds aren't going to arrange them. Odd numbers do not generally arrange themselves symmetrically. And then if you have the last element is an even number, you're going to have a symmetrical shape, and it is going to be nonpolar. Let's check that out. 4. Okay, so the last number is an even number and nonpolar. Okay. Odd number, polar. Even number, nonpolar. Let's see if it works, right? So over here, there's a 3. Odd number, polar. And even number, nonpolar. So then since this is just a 1, that's an odd number. So that is going to be polar. And then this ends up in a 2, even number, nonpolar. Okay, so that's Lewis dot structures and molecule polarity. I know that's a lot, but you should be able to draw each of these. These are the most important ones that you should be able to draw. All right, until our next video. Keep practicing these. You should be able to draw these in and out. Very popular short answer question on the Regents exam. All right, good luck. Ask questions of your teachers just to make sure if you're stuck on anything.